Hello and welcome to Rudy's Electronics Lab. Today I'm going to show you how you can self-calibrate the time base, so the internal clock frequency reference standard clock of the Rohde Schwarz RTB2004. In the last couple of videos I've already been working a little bit on measuring different devices and its internal clock, and when I was measuring a lot of devices I found that the RTB clock is slightly off. I mean, it's still very nicely within the 3.5 part per million ppm limits that the specification sheet gives, but I think it can be tighter basically, and today I'm going to show you how you can basically do that yourself. And we got a couple of things to make that possible. I got a frequency counter here. It's actually the Siglent SDG2000X series of signal generator, but we're using it as a frequency counter today. I got another oscilloscope. I'll tell you in a moment why I'm having another oscilloscope here. I got here a nice tiny new device, the tiny frequency and phase analyzer. We'll see how useful that is to do this. And there is the Leo Bodnar frequency reference that I'll talk about in a moment. If you want to do this yourself, you're gonna and wanted to do it a similar way as I do, you either need a second scope or you need something like the tinyPFA, because we will see that actually the frequency counter is not accurate enough to do the job of today. So we're starting basically with taking a reference signal from the Leo Bodnar GPS disciplined oscillator. It's over here. I made a couple of recent videos on it, and I believe it's by far the most accurate signal that I got into the whole lab. No doubt about it. So that will serve as my standard, basically my reference in order to calibrate other devices. So it's coming in here basically on the oscilloscope, a nice steady waveform of 10 megahertz, and it's coming in here basically as reference in for this, so the counter will be correct, and it's coming in as reference on one of the channels on the tiny PFA. Now the first thing we'll need to do on the Rohde Schwarz is basically send out its 10 megahertz reference signal, so we can start to compare it with other signals. So I'm going to go here to the menu. I have to go to setup. I can go to auxiliary and I can choose for 10 megahertz, and that basically means he's going to send out the clock frequency, the 10 megahertz reference on the output. There we go, and we go back. Yeah, so what we basically see here, we see here 10 megahertz appearing, and we also see some wild waveform over there. Let's make it a little bit smaller, right? So it's clear that it's not the same frequency, because it's kind of jumping wildly. If I would just take a single shot, it's almost the same frequency, but it's certainly not exactly the same frequency. So we need to get it closer. What we see here on the frequency counter, basically, he is jumping between 10 megahertz and 10 hertz and 10 megahertz and 20 hertz. This is the issue, is even a little bit worse than I thought in my previous video. This one is jumping between 10 hertz higher and 20 hertz higher. So I don't think it can actually believe a single hertz measure a single hertz difference here at 10 megahertz. Only steps of 10 hertz. So the accuracy is lower than the number of digits seem to suggest here. So the frequency deviation is jumping between 1 and 2. I cannot get at anything more precisely, and I don't really trust the average, because I think it lacks in precision when measuring it. So this is not going to be very useful here. We have to rely on the two other devices here. But anyway, that will work. So no worries about it. But there's an important other step to take now, because how do we get to set the reference frequency of that unit? That is not described in the user manual. It's even not in the service manual, which is not a public document in the first place. It's not on many other sources, but actually there is a menu for it, and it's a command. And what you have to do is you have to send the command basically via the SCPI, the Skippy device control interface. And I'll show that right over here. And I'm sending it now to my unit. 1, 2, 3. And look at that. What's happening here is a hidden menu coming up. And in this hidden menu, we can choose channels, trigger, reference frequency that we're looking for, logic probes, generator adjustment. We can see the temperature sensors. Let's take a quick look here. We can see how warm everything is in the device. Okay. Self-alignment. Self-alignment is the only one that you can read from the regular types of menu. The other ones are only from this hidden secret type of menu. And we want to change the reference frequency. So we go here, we click, You always have to click it twice, don't know exactly why. I'm here, and it's now at its reference value of 128. What is this value doing? I believe this is connected to a digital to analog converter, so there's a voltage come out of it, and that voltage basically goes to the crystal. So the crystal is being biased by that voltage, and you can make it click a little bit faster or slower by varying that voltage. And that's exactly what we're going to do now. So we need to bring it down a little bit. We know from here it's a little bit too high, and actually bring the frequencies close together. So I'm going to click on this value. I'm going to click here on the button. It's a little bit counterclockwise. I have to turn the button the opposite way than I'm normally used to on this device. I have to turn to the right basically to... you see, we're getting closer here. We still see here, I'm getting to that in a moment, still closer, still closer. This is faster again. This is the closest I can get. So now the signals are pretty close together. And actually my analyzer tells me basically about the phase shifts really taking place here. And so this is interesting. He's showing me the frequency difference that he's measuring, but also the phase shifts. And ideally, if the frequency is exactly the same, there will be no phase shifts forever. However, the larger the different frequency, the more occurring are the phase shifts. And you see here this blue line in the device, it became very rare. If I go to another value, you see there are going to be lots of phase shifts here. But if I'm going over here, fewer phase shifts. And I think in this mode, even fewer than that. Do you see that? Now we're getting very close here. Very few phase shifts, and also on the Siglent oscilloscope. So this is the right value. We're now very close. We can once more look over here, but again, we already found that this unit is probably not very good at doing it because he doesn't have the right resolution to do our exercise, but the other two instruments are doing it. You might be wondering why I'm using another oscilloscope, why I'm not using the oscilloscope right over here. Let me first accept here the new value, and he's going to remember that. So next time I'm going to turn it on, he's going to be exit. I'm going to go out of this menu altogether. Why am I not using this oscilloscope basically to show these two waveforms? Well, I can do that, but unfortunately when you go to the calibration menu, he switches all the settings and he goes to the shortest time base and he goes to the most sensitive input, so the input is clipping, so you cannot use it as an oscilloscope at the same time as you're doing the time base adjustment. So this is just one thing to know, but anyway, as long as you have some other oscilloscope or any other device like the one over here, which I find very cool, you can basically do exactly what you want. So now we got it calibrated exactly the way we wanted to. Now, that's the end of this short video. I hope you enjoyed it, and do check out my earlier videos on this topic, and subscribe to the channel, and see you next time at Rudy's Electronics Lab.